Hello everyone, in this part I want to give the idea of line integrals of curves. Before going further, let me remind you the idea of area and volume. From calculus 1, we know that how do we compute the area under y equals f of x from the point A to B. We choose a length, let's say dx, since this is the interval of x, and we compute the area of this rectangle. Summing up all these areas from A to B, as you see, this is f of x, this distance is f of x, integral of f of x from A to B, in f of x times dx, f of x times dx gives the area of this rectangle, and summing up all these areas give the area under the curve f of x. And this is the idea of single integral from calculus 1. From calculus 2, we had a surface, something like this. Okay, we had a surface, and we computed the volume under this surface by double integral. Okay, double integral over the region D of f of xy dA. Okay, it is the idea of double integral. Now, what is the idea of line integral? Let's say we have a curve which is represented by a parametric equation, x equals g of t, y equals h of t, and t is in between a and b. Okay, so when you give the point A, you have g of a for x and h of a for y. Let's say this is the curve. This is the parametric curve. Okay, so initial and terminal point. So for the point A, you have g of a and h of a. G of a is here and h of a is here. And using all these points in between a and b, you have this curve. You have this parametric curve. And let's say we have the surface f of xy. This is the surface f of xy here. Okay, now I mark or I point each corresponding point on the curve. X equals g of t, y equals h of t. So for instance, the corresponding point for the initial one is this. Okay, and if you continue to draw all corresponding points of the given parametric curve, you have this curve on the surface f of xy. And the aim is to compute the area of this wall. So which wall actually? Let's say you have a fence or wall from the upper curve to the lower curve. Okay, from the upper curve to the lower curve, something like this. Okay, something like this. You have a surface, you have a wall, or you have a fence, and you want to compute the area of this fence or the area of this wall. So how can we figure out the area of this curvy looking wall? It is the aim of, it is the idea behind the line integral. We first have, actually we have the analogous idea when we compute the area under a curve. What do we do here? We choose a length which is called dx and the corresponding f of x, and we multiply by this to obtain the area of this rectangle, and we sum up all these areas to have the area under the curve f of x. So I will exactly use the same idea here. I choose a length of the curve which is ds here, ds. Let's say this super small change in the arc length, in the arc length of the curve, and let's call this length as ds. Okay, then we have a straight line from the lower curve to the upper curve, and then we have a rectangle, as you see. So how do we compute the area of this rectangle? And as you see, this the upper point is, how do we know the upper point? It is f of xy. Since it is on the surface, it is on f of xy surface. Okay, and this point is f of xy. So if you multiply f of xy by ds, this super small change in the arc length of the curve, then you have the area of this rectangle. Summing up all these areas from the point A to B, you have the area of the curvy looking wall from the upper curve to the lower curve. Okay, so the remaining part is that how do we compute ds here? What is ds? Now let's look at this graph. Let's say this is ds, the same ds here, okay, and this is our x-axis, this is the y-axis, okay, this is the y-axis. From here, this is x, this is y, okay. So, and ds is there. Since you have x-axis, this length is called dx, which is this length, and this length is dy, okay, dx, dy. The change in x-axis, dx, the change in y-axis is dy, and ds from Pythagorean theorem, dx is the square root of dx square, ds is the square root of dx square plus dy square. So let me write this expression here. Integral from a to b of f of xy, instead of ds, now I have square root of dx square plus dy square. Okay, now let me continue. This is equal to integral from a to b of f of xy. So instead of this square root expression, actually let's multiply and divide numerator and denominator by dt square. dt square divided by dt square times dx square plus dy square. And this is equal to integral from a to b I'm sorry, let me multiply this d by dt, and this is dt square divided by dt square. Okay, I think this is the same. So this integral is equal to integral from a to b, integral from a to b. Let me clear this part and write here. Integral from a to b of f of xy. Okay, so this is x prime of t square plus y prime of t square dt. And don't forget that the parametric curve is given, the curve is given by a parametric equation. X equals g of t and y equals h of t. Then it is the curve is also given, and it will be requested to find the line integral of that curve. Using this formula, it will be very easy to compute the line integral of a given curve.